So today I'd like to present something related to the peat fire. So it's kind of a smoldering fire, which I have started to do the research since my PhD in Imperial College. So this particular topic is actually part of my PhD student Xiaoren's thesis. So mainly focusing on how the peat, especially these frozen peat, burning in a very cold temperature, and how the global warming is promoting the carbon emission generated from the peat fire by increasing the environment temperature. And this work was published in the Science and Total Environment. So let me give a very short introduction about the peat fire. So this is an example in the tropical region in Indonesia. And essentially, you can see the entire forest is burning, but you cannot see the flame. So that's a problem, because what's really burning is on the ground, actually below the ground. So for the region, you cannot see the smoke. There may still be fire burning like deep into the soil. So this kind of fire is a smoldering fire. So essentially, these are peat fire. And you can imagine for such a large scale fire, such a long lasting fire, will generate a lot of smoke. So if we look at this fire from the space, if we look at the satellite image, so this will be the smoke motion you will see. So all these red points are essentially the hotspot. And these smoke are generating from the Indonesia. And you can see the smoke will propagate to Singapore, to Malaysia, and even to other countries. So that's the scale of these kind of fires. It can last very long times, weeks, or even months. So if you have been to Singapore in the summertime, so unfortunately, sometimes there will be very big haze. So these haze are essentially generated from the peat fire in Indonesia or Malaysia sometimes. So sometimes I compare this haze problem with the haze problem in China. We also have a lot of pollution issues in China. And although they seem different, but fundamentally they're quite similar, because all these combustion smoke are a result of incomplete combustion. So for the peat fire, essentially the peat are not fully burned. They generate a lot of these aerosols and PMs. And same for the car engine, for the power plant. If you don't burn them completely, they will generate these particles, can generate haze. So fundamentally, the reason for this haze is incomplete combustion. So one of the largest fire, peat fire, we have seen in the tropical region is in 1997. So it has been estimated about 13 to 40% of man-made carbon emission was generated by that single fire that lasted for at least 2 months. And this NASA diagram shows the smoke motion and the density of the smoke during that fire. So we have been looking at a lot of these fires in tropical regions. But if we look at the distribution of peatland, look at the global distribution. So we can see, in fact, there is a lot of the peat in the northern region. So if we look at the map, essentially most of the peat are accumulated either in the tropical region, especially in Indonesia, Southeast Asia, and also in Northern Europe, Russian, and part of Northern China, as well as American Canada. They have a lot of these peatland. In fact, I would say the Boreal and Arctic peatland has more peat compared to the tropical regions. But comparatively, we pay relatively less attention to the northern peatland. And about 1/3 of the global soil carbon actually stored in the peat. So it's a big carbon sink if you think about the global carbon footprint. And if we look at the peat fire incidents over the last 20, 30 years, and we found that there's a lot of fires, particularly in the Southeast Asian. There are some fires in Russia, UK, or Canada, Alaska, or East United States. And but we have a lot of peatland in the Arctic region, the cold region. So where are these fires? So I think one of the reasons these fires in the northern land are not really get attention because not a lot of people living there. So they are not severely jeopardized by these peat fire. So that's the reason people care a lot more about the tropical peat fire, because we have a lot of people living there. But the reality is we have more and more Arctic fires now. So I'll give you an example. So this is a photo in the Arctic region in Russia. So you can see it's basically covered by the snow. So the entire region is covered by snow, and you can feel something is burning below the snow. This is like minus 30 degrees Celsius. So what's really burning is the peat below the snow. So you can feel how intense these fire could be and how persistent these fire could be. Even these heavy snow cannot stop it. They still burn there and last forever almost. And another thing I have to emphasize is when you don't see the smoke there could still be fire burning below it. You just didn't see it. So this is a problem I'm trying to talk about today. And another recent study shows there's a clear overwinter fire in the Arctic region. If you look at the satellite image, you can see the fire actually come out in the next spring because of the warming surface. So the reason is the fire never really extinguished, although you didn't see the smoke spots. So this is how persisting these fire is, and many times you cannot really detecting it. You cannot really know if these fire are extinguished or not, or if they exist or not. So that's how difficult to handle these peat fire. And if we look at the typical wildland fire, we can divide them into two types. First is a flaming fire on the surface, could be crown fire, and these fire are very hot. The flame temperature can over 1000 degrees Celsius. But for the peat fire, it's typical smoldering fire. And one of the best examples for smoldering is the cigarette, the burning cigarette. So you don't see the flame, but you see something is burning. It generates a lot of smoke, a lot of heat. And the temperature is relatively low. The maximum is like 600 degrees Celsius, but if you look at the fire deep into the ground, so maybe the fire region is 600 degrees, but on the surface, maybe there's only 50 degrees Celsius. So you cannot really feel there's fire burning there. And they are very easy to ignite, but very difficult to suppress. Part of the reason it's difficult to suppress because you don't know whether you have successfully suppressed it or not. So that's the challenge part. And what is peat? Peat is essentially the decomposed the vegetation. And if you give them a little more, like another million years, it eventually can become coal. So sometimes we say the peat is also young coal. I know like Norway, Ireland, they also burn these peat in the power plant because it's essentially their coal. So for this kind of peat, they have a lot of carbon installed there. If we just release a tiny bit of these carbon from the peat through the peat fire, so we can imagine the scale of it. It could be comparable to the human carbon emission. So it has been estimated every year, the peat fire carbon emission is almost equivalent to like 10% of the global man-made carbon emission from burning fossil fuel. And these carbon emissions won't disappear like flaming fire, because we know the tree grows faster, very fast. They absorb these carbon dioxide, and quickly. But these peat, they take thousands of years to be formed. So essentially, they are net carbon loss. So you won't have these fire, these carbon come back to the soil in like 1,000 years. So the problem is we have a lot of carbon emissions, so we push the global warming, and the soil become warmer, and it will be easy to ignite. So in this talk, I'm mainly talking about how the warming weather actually increasing the fire in the peatland. And another important thing to remember is when we talk about the global warming, we talk about the global average temperature, not really the Arctic region. For the Arctic region, they actually warm in a much faster rate than the global average. So if we look at this nice video showing the variation of the polar region, you can see they actually moving in a much larger variation compared to the other region. So they are more sensitive to the global climate change and global warming. So this is something we need to remember. They actually warm much faster than the average condition. And for the permafrost, so it's not a constant temperature. It actually changes temperature with different months to different seasons. So in the winter time, the surface temperature could be much lower compared to the ground. But in the summertime, because of the heating from the atmosphere, so the surface temperature actually is higher than the deep layer temperature. So you actually will have a temperature profile decreasing with the soil. So and in the summertime, that's most fire risk seasons. And if more of these permafrost defrost, then there will be higher chance to have a fire. So the purpose of today's research is to identify the limiting temperature for the peat fire to burn. And also using that probability, we can estimate how deep the fire can go and how much of the carbon can it release. And then we can predict under different global warming rate, then how much carbon emission will be generated. So that's the purpose of our research. So what we do is a very simple and small scale experiment. So we bought some peat from Estonia, and we put some of these samples, and we dried it and also wet it into different moisture content. Then we put these peat into a small combustion reactor. Then we put that reactor into our freezer. So this freezer is have like 200 liter volume, and it can change the temperature from minus 50 degrees to positive 50 degrees. And we keep the air flowing, and also put a lot of ice inside to ensure the environment temperature does not affect by the fire. So our goal is to find the minimum temperature for these peat to burn. And so this is the temperature data we get in our experiment. So if we put the temperature to minus 5 degrees Celsius, and the peat moisture content is 25% in mass, we found that the fire is very robust. The peak temperature can go to 550 degrees Celsius under such an environment. And then if we increasing the peat moisture, we make it wetter, make it to 75% weight fraction. Then we found that, okay, the ignition is okay, but the fire cannot sustain itself. So by this experiment, we can find the limiting moisture content is something between 25% to 75%. So we do that for different temperature. Eventually, we get this very nice temperature threshold. the fire threshold for the peat. So we can see that the y-axis is the environment temperature and the x-axis is the peat moisture content. So if we increasing the environment temperature, then there will be higher chance to fire. And if we lower the temperature, increasing the moisture content, then there will be higher chance of no fire. And the limiting condition is showing here. And we found that the peat is able to burn at negative 40 degrees Celsius, as long as its moisture content is low, as long as the peat is relatively dry. So that actually makes sense why the peat actually can burn below the heavy snow. So for example, if the temperature is 0 degrees Celsius, so below that would be the permafrost. So if the moisture content is like 70%, it still can burn. Okay, so that's a limiting condition. And for the boreal peat soil, usually we search a lot of literature. We found that the average moisture content is about 82%. So in other words, if we have the soil temperature about 6.5 degrees Celsius, then the fire can burn. So that's the principle of this fire threshold diagram. Then we just apply this diagram into the soil temperature profile. So we use the data in 2015. So the soil temperature will, in the summertime, I'm talking about, will decrease with the depths. So the deeper the soil, actually the colder will be. This is in the summertime. And in that case, we know the moisture content is 82% moisture content. So there will be like 1.13 centimeter of the peat will be consumed. So if we have global warming and the temperature will increasing after many years, for example, in 2050, because the environment temperature keep increasing, then the soil temperature will also increase. So in 2050, if there is a fire, there will be 25 centimeter of the soil will be burned. And if we keep increasing the Earth's temperature to the end of this century, we will have like almost 60 centimeter of the fire will be consumed. So this is under the current Arctic warming rate of 0.44 degree per decade. And with this data, we know the depth of burn, we can estimate the carbon emission. And one of the important data we found is that the probability of these Arctic peatland burn is about 0.5%. So in other words, we can estimate every year how many of these peatland will be burned, which will be 20,000 kilometer square per year. And with this data, we can easily calculate. So for example, in 2015, in the entire Arctic boreal region, there will be 143 megaton carbon loss. And that number will triple by the end of this century. And if we accumulate the entire number, we will find that the total carbon loss in this century will be 28 gigaton from the Arctic peat fire. That is equivalent to about 2 to 3% of human carbon emission by burning fossil fuel. So we know this is a very rough estimation because actually there's a lot of argument about what's the warming temperature in the Arctic region, but it's okay. We do a sensitivity analysis. If we warm the Earth at different rate, if conservatively, if humans do nothing, they don't do any renewable energy, no carbon footprint reduction, then we may increase even faster. So in that case, we may have even more carbon loss. If our human beings do a lot of things to reduce the global warming rate, then we may have a lower carbon loss. So under different carbon rate, eventually we will find if you have a larger warming rate, you will have higher carbon loss. If you have a low one, you will have less one. So this is essentially estimation based on the fire threshold of the peatland. And it's very challenging to detect these peat fires. There are maybe a lot of methods can be used, but most of these methods are used for the tropic peat fire. What if we are dealing with the Arctic peat fire, which are underneath these snows? Then it will be very, very challenging. So how to detect it is a very big issue. Another thing is how to suppress these peat fire. It's not so easy, I guess. Essentially, we can do 3 ways to stop a fire: removing the fuel, removing the oxygen, removing the heat. But this is also very difficult by human beings. If we look at these firefighters fighting the peat fire in the field, it will be very cruel to send people there to fight these fires. It's essentially so dangerous, I would say. And another thing is, in the tropical region, we can wait for the rain, because there will be always heavy rain to stop the fire to a certain degree. But what about in the Arctic region? There's no rain. There's a lot of snow, but I doubt if the snow is really helpful to stop the fire. So these are all the challenges we are dealing with. So in short, so I want to make a summary is the peat fire is the largest fire on Earth and cause a lot of carbon emission. And we also using a small experiment to demonstrate the peat fire can actually burn in -45 degrees Celsius. And using this fire threshold to estimate the carbon emission every year, and also the carbon emission in this century under different heating rate. So it's about 2% of all the man-made carbon emission. And that's all my presentation. And thank you for your attention.
Well, thank you very much, Xinyan, for a fascinating presentation. I can hear a little bit of an echo here. I hope you won't. Yeah, any questions? Gabriel, I can see you have a question. Andreas, I don't know who was first. Let me go with Andreas first, perhaps.
Oh, thanks. Huang, brilliant to finally see your face. I've read your papers before. I love them. So thanks. Great work. One question. You mentioned you had dried the Estonian peat first and then re-wetted it. I think there might be an issue insofar that water repellency will kick in. You might measure a moisture content, but it might actually be not the, I switch on the camera, content. Maybe you can see I'm doing content, because you will have changed the ability for water to go into the fine pores, I think. So it might be better, or would be interesting, to repeat some of that. Maybe it's a big effort, I know, to go the other way, to have completely re-wetted peat and then dry it out. And I bet you will find a different response. It might not vary that much, but it would be interesting to test. But very good. And I leave that with you. But the interesting aspect I wanted to ask you is in relation to UK fires, for example. Your graph is so fascinating of the relationship between temperature, soil moisture content, and fire ignition potential. And I think translating to UK peatlands, even re-wetted peatlands, to me, look highly vulnerable to peat fires under that scenario, because moisture contents, even in intact peatlands, can go down to 60–50% over the first 30–40 centimeters during a summer drought. So to me, that looks highly combustible. Have you thought about that?
Yes, if the moisture content is like 60%, then that's very flammable. Not flammable, yeah. Combustible.
Yeah, combustible. Yes.
Yes. So we found that usually you need to have like 150% to stop the fire, and more recently we think well, different peat are very different. If the density of the peat is higher, then they could be more combustible.
And about, interesting.
And about the water rewetting, I think that's a very important point, because every time we write something about this, they will be criticized about the method we use. So recently we started to have to use like a dry at different stage and try to keep it more naturally.
Yeah.
But for this work, I think if you put the peat into the freezer, eventually they become like ice brick. So it doesn't really matter in that sense.
Good. Yeah, fine. No, and it's not a really deep criticism. It's just an observation. It would be interesting to test. But no, really nice work. Thank you.
Thank you.
Gabriel. And can you come close to the mic? You were actually a little bit hard to hear earlier. You're mute at the moment.
Is it?
Yeah, now we can hear.
Okay, sorry. Yeah, I second everything that was just said. I was wondering about a detail that I might have just simply missed. So in your kind of future climate scenarios that are really scary, I was wondering, did you account for changes in precipitation and therefore changes in soil humidity? Or can you even account for that?
We can account for that, but we don't have the data. So yes, there's a lot of papers about whether the global warming increasing the soil moisture or decreasing it. So there's a lot of arguments. So so we just pick a fixed value, but it can be recalculated. For
so what would be your gut feeling? What would you think would happen, especially in those, let's say, very northern peatlands in let's say Russia, Canada, and so on?
Well, I'm not an ecologist, but my guess is, I think it may actually become wetter, the soil.
So there's a little bit of hope, maybe.
Yeah.
Thank you.
Thank you.
Okay, in the interest of time, I suggest we do move on, but hopefully we will have 20 minutes or so at the end of all the presentations to discuss this together and ask questions to individual presenters. But thanks very much again, Xinyan, for a fantastic presentation.
Thank you.
So let's move on to our next speaker, Dr. Tian Quinn. I hope I pronounced this correctly, Tian from the Institute of Botany.